Hello? Hi, can everyone hear me? Perfect. So welcome to my session, which is the real-time data science with Azure Cosmos DB. My name is Andrew Ho. I'm a program manager for Azure Cosmos DB. I joined the team a little over 3 years ago, so I'm happy to actually give this talk just because I think this is something that's relatively new, as well as it's very cool on how it interacts with Azure Cosmos DB. So I'm happy to shed some light on the data science aspect of it. For this talk, I'm going to talk a little bit on Azure Cosmos DB in general, so I'll spend about 15 minutes on that at the beginning. I'll dive into some of the data science aspects of it, some use cases, and then I will take some questions at the end. Before we get started, I just want a show of hands of how many people attended my overview session. Okay, perfect. So I'll go a little bit more in detail for the overview part for Azure Cosmos DB, just to get everyone on the same page. Okay, and we can begin. I think the last couple of people are starting to take their seats. So global applications these days have a number of requirements for them to launch, as well as to support the number of customers they have. Some of the requirements are they need global distribution, elasticity of compute and storage, fast, responsive millisecond latencies, as well as they need a durable, consistent, and highly available database. So how does Azure Cosmos DB fit into that role? How does it set itself apart from all the other databases out there, and why is it very unique in that aspect? So one of the core value propositions of Azure Cosmos DB is its global distribution. We set this a little bit apart from geo-replication because we use the underneath replication used with NoSQL databases in order to replicate that data across multiple regions. So what does this mean? This means that you can have a worldwide presence of your Azure Cosmos DB database in any number of regions that Azure supports. I believe that's over 40 now regions that Azure has a presence in. We are a Ring 0 service. That is an internal term we use inside to mark the priority order of onboarding of services to new Azure regions. As you can imagine, because this is such a core service and the premier NoSQL database of Azure, you'll find that there are a lot of services built on Azure Cosmos DB, which means we are highest priority when new regions do come up. Some of the other things we do support is automatic multi-region replication. The state of the art before was setting up replications very difficult. We've really simplified that so that you can go into the management portal, click on any number of regions you want, and you could replicate to anywhere around the world with just a couple clicks. We have multi-homing APIs. Multi-homing APIs are that when your application is interacting with your database in one region, yet a disaster happens in that region, it will automatically fail over to the next region. A lot of databases out there require new deployments so that you can put a different endpoint in and adjust your database accordingly, as well as your application accordingly. But for Azure Cosmos DB, we have that logic inside the database as well as the driver so that we have that automatic failover, as well as the multi-homing APIs. We have manual and automatic failovers. This means that you can trigger a failover for BCDR purposes, any type of business continuity disaster recovery, and we're designed for high availability. One quick interjection. If you do guys have any questions, feel free to hold them until the end. I will be trying to go through this very quickly so we can enter some of the meat of the stuff, which is the data science aspects of it. Low latency. Low latency is another value proposition for Cosmos DB. We want to make this one of the fastest databases out there. We do at the 99th percentile deliver guarantees on how fast your database will be. It's less than 5 milliseconds for reads on 1 KB documents and less than 10 milliseconds for writes for 1 KB documents. And we do put an SLA on it, which is our promise to you guys. As always, we do have synchronous automatic indexing so that you can have high ingestion rates of writes and your data is automatically indexed while that's happening. What does that mean? Your data is available to you to query upon as soon as you write it. There are databases out there where when you do write your data, it'll be indexed later on, which means it's not really valuable to you until it's fully indexed and your queries work on it. We have multiple well-defined consistency levels. The state of the art before for most databases, at least most NoSQL databases, is you have your strong and eventual. for consistency levels. We've added 3 more in between, which are bounded staleness, session, and consistent prefix. I can go a little bit into detail afterwards if you guys do have questions on this. Elastically scalable storage and throughput. Modern applications these days require your application to grow, and it requires a database that can grow in conjunction with the application. As you can imagine, any application out there, as the data grows, as the number of users grow, your database needs to be able to handle that. So we are elastically scalable, both in storage as well as throughput, right? So a database that grows purely in storage but can't handle the number of reads and writes might not be that useful. A database that could only handle a lot of reads and writes but can't scale in storage is not very useful. So we have both of it, and both can be adjusted independently of one another. That's incredibly nice because applications come in many different sizes and forms. There are a lot of applications out there that only have a small amount of data but have lots of reads and writes going against it. There are other applications out there that are much colder where you don't have that many reads and writes coming in, but you're storing tens, hundreds of terabytes, petabytes worth of data. And so Azure Cosmos DB is built for any of those use cases. And a neat feature we have on top where we have a time to live feature, which essentially means that as your data grows, you can dictate when you want the data to be expired out or deleted. There are a lot of users out there who set it to a year, 2 years, 3 years, 4 years, 5 years, so that they can keep their data within a maintainable size. So multi-model, multi-API. For those of you who followed the launch of Azure Cosmos DB, you guys do understand that this is what kind of revolutionized databases out there, where we're able to support different types of models, and we have different APIs against those models so you can interact it in a very familiar way. So some of the models that we do support right now are our graph, document, and key value. And the APIs we have on top of it is MongoDB. We have a SQL-like syntax, as well as we have Gremlin for graph and table storage for those of you who use Azure Table Storage. And this is kind of our promise to our users that we will be building more APIs and models on top because we want to make it as easy as possible for you to use Azure Cosmos DB. A lot of databases out there will bring their own proprietary APIs, which lead to a couple things, either vendor lock-in because it's difficult to change your applications, or a lot of ramp-up time and learning curve, right? You have to understand the database. And so we want to simplify that as much as possible, get as close to our applications as possible and users as possible. Schema agnostic and automatic indexing is another big value proposition. We do have a white paper out there that documents how this is done and why it's so special compared to others for those who are interested, which means that we can support automatic synchronous indexing for flexible documents, which means as you put in data with different structures, with different schemas, we can still, at a very high, fast rate, index everything, have it available to you within less than 10 milliseconds for the 99th percentile. This is what makes us so unique. This is what allows us to hit a lot of the latencies, as well as be flexible enough to support different models and APIs. SLAs. We've changed the game a little bit in Azure, as well as all database services and cloud services by delivering 4 SLAs now. You have your primary one, which is availability, the one that most people care about, and we support 4.9, so 99.99% uptime, and we're getting closer to 99.999%, and we want to make sure that as a foundational service, as your database, we're there for you, as well as you can trust your database, which is also why we've added the additional SLAs. For those who are not familiar, SLAs stand for service level agreements. They are our promises to our users, our customers, as well as these are financially backed. So if you miss any of them, you could come back to us saying that you didn't keep your promise, we want a refund. And so we want to put our money where our mouth is and deliver you the best service that you could trust possible. The other SLAs we've added on are the low latency. Some of the numbers I mentioned before at the 99th percentile, we have an SLA on that. We have an SLA on consistency. I didn't dive too deep into consistency just because I do want to move fast in this part, but we do give a guarantee on consistency as well as throughput. We guarantee that all the throughput you've allocated for your database is guaranteed to be there so you can use it whenever you want. And the key thing is we expose all these metrics in the portal so you can keep us honest. Because we've had a number of people say, well, you have all these SLAs, but we have no idea if you're keeping it or not. And we have to build a lot of infrastructure to make sure that you're keeping it. And so we actually expose a lot of the SLAs in the portal so you can actually check it out to make sure that you're keeping us honest. Security and compliance, another big thing. And so we have a lot of security features out there for your database needs. We have encryption in motion, encryption in transit. We have fine-grained row-level authorization based on users and permissions. We have IP firewall rules, as well as for the compliance certifications. We have ISO, EUMC, which are the European model clauses. We have the HIPAA for health. We have PCI for credit card information, and SOC 1 and SOC Type 2 for financial information. So total cost of ownership. This is a fairly unique slide. This slide talks about a white paper that DynamoDB released on how much cheaper they were compared to a lot of the other on-prem NoSQL services. So we replicated their experiment, and we published our own white paper, and we found that we're about 3 times cheaper than DynamoDB, and significantly cheaper, 10x cheaper than on-prem services. Some of the reasons that contribute to this number is primarily because on-premise services are machine-based, so you have your database instance running on a machine, while we are multi-tenant. So we can have multiple users all sharing the machine, and all that coordination is handled by us. And we make sure that this is possible by having strong resource governance. So resource governance is how we're able to allow you to use these machines and yet dictate that there are no noisy neighbor problems, right? The noisy neighbor problem is, well, I'm on the same machine as that guy, and he's using all my CPU, which means I'm not able to use my database. So we make sure we have strong resource governance, and we use that in a predictable manner so that we can deliver you the full experience of what you've actually allocated for yourself without experiencing the hassles of the noisy neighbor problem. And lastly, the one that we're going to talk about quite a lot in this talk is the Spark integration. We announced our Spark integration, I believe, almost half a year ago. And this integration has really unlocked a lot of different opportunities for applications. The connector right now is in public preview, fast moving to GA, which is general availability. It supports the RDD and dataset-based connector, or it supports a native integration with Spark SQL, direct mapping to the Cosmos DB partitions, which I'll talk about a little bit later. It natively leverages Cosmos DB's indexes for performance reasons. It has predicate pushdowns. I'll talk a little bit more about that as well. And like I mentioned, the GA is coming up very fast. So why is this service integration so important? Well, the overall thing is the database is just one component of your application. Database is just one aspect of the full suite of services you'll be using, which means that we want to make sure that we can give you a rich, predictable application behavior as well as functionality across many Azure services, which is primarily where I'm going to talk about how just the integration of 2 services, Cosmos DB and Spark, can unlock a lot of different opportunities for your applications. I hope to unlock a little bit of thinking and brainstorming on how this can influence your applications as of today. So I'll talk about a couple scenarios where you're able to use distributed computing with distributed database. And some of our customers, as of today, they use a number of services together to make sure that they can deliver a rich experience. You can see right here that Skype uses Azure Cosmos DB, but they also use Traffic Manager, as well as a number of other services to give you that kind of performance. Toyota also uses us for IoT purposes with a suite of services as well. Jet.com, an e-commerce site, also uses us as well to deliver their sales and their events. And so they use a suite of services. And the key thing for Jet.com, which I like highlighting, so I'll slow down just a little bit here, is that they like using the elastic throughput of Cosmos DB in both aspects, right? And so everyone starts to think, oh, if it's scalable, it can grow, grow, grow. But the other aspect is you need to shrink if you're scaling up for a certain event, right? And when it comes to e-commerce sites, the biggest event, Black Friday as well as Cyber Monday. And so they're scaling up for that and scaling down afterwards in throughput so that they can adjust for customer demands and user demands. The Walking Dead official game uses us as well. They use a suite of services as well, depicted in the architecture diagram. And so now we'll head into the Apache Spark to Azure Cosmos DB. So this is kind of the meat of this presentation, where I'm going to talk about the data science parts of integrating Spark with Azure Cosmos DB and what kind of opportunities it really unlocks for the users. So we expose the connection from Azure Cosmos DB to Spark in two ways. First, we do have a PyDocument DB library out there that connects. This is fairly useful because you're able to use Python natively, but the interaction model right now is the gateway interacts with the master node of the Spark clusters. What does that mean? That means that as you issue a query from Spark all the way to Cosmos DB, it goes into our gateway node, which talks to the individual machines and says, here's the query, and retrieves the data and ships it back. So overall, this is not a bad design. You can use Python on how you want to use it, the native Python library. But the one risk is because you're going through a single machine, the gateway node, as well as the master node within Spark to do all the orchestration, it's better for smaller data sets, right? And so this is a smaller result data set, not so much of overall data set. So one thing I do want to highlight is, with the integration, you can issue a query over from Spark to Cosmos DB to reduce the amount of data you send over, which means the result set can be very small, which means your Python library could be very useful in that case. But overall, we like to promote our other one, which is the Spark Document DB Java library, the Java connector. So the Java connector can actually go issued to the gateway node, figure out what the individual partitions are, and now has mappings of the mappers within Spark to the actual partitions within Cosmos DB. So this is something I really like highlighting because just because when you have this connection, you have a distributed database connecting to a distributed compute. You can have the machines within Spark connecting to the actual partitions within Cosmos DB for fast ingestion rates as well as fast writes. The initial kind of acknowledgement across both of the services or the Spark open source platform is that you first go to the gateway and it'll tell you what the individual partitions addresses are so that it can address it afterwards. And this is much better for the larger data sets, and this is the one we promote more heavily. So what are the advantages of using Azure Cosmos DB? So one of the advantages of using Azure Cosmos DB is Azure Cosmos DB is designed for high throughput and low latency, which means for IoT scenarios, it's very, very useful. For IoT scenarios, you have highly concurrent ingestion of data, let's say weather data, safety alerts, flight information that can all be sent over to a persistent data store like Azure Cosmos DB, and then can be relayed over to your device notifications, some type of web REST API. Let's say if you have an application that uses this, and it could also be shipped over to your Apache Spark or Azure Machine Learning for insights and data science purposes. Some of the key things is Azure Cosmos DB can take updatable columns. So as you're writing data into Azure Cosmos DB, let's say you're logging flight delays. Well, your flight delays change very frequently. So you need a database or persistent store that can actually have updates shipped to it and update the documents, which is possible within Azure Cosmos DB. So right here, we show you the delay of -30. The delay of -30 can be, for negative numbers, for those who are interested, could be that your flight actually left early. The next thing is we actually support pushdown predicate filtering. So pushdown predicate filtering is essentially you can take a query that runs on Azure Cosmos DB and send it through the connector to filter your data, transform your data, which is very useful because the data sets you'll normally be working with in Azure Cosmos DB can be very large. And so if you want to filter out different properties, if you want to adjust your data, you can send that query to Azure Cosmos DB. And as always, since we do have the schema-agnostic indexing, the data within can take advantage of the query language on top of the schema-agnostic indexing to filter out your schema list data. So I will head into a demo. For this demo, we'll talk about the flight performance across many different delayed flights within the United States. We'll run some different Spark jobs on top of it, as well as we'll run some simple ML algorithms on top, simple logistic regression algorithm to predict delays, which is very cool. So the first thing I'm going to showcase right here is how the data looks like in Azure Cosmos DB. Can everybody see this? Perfect. So it's very simple data. You have a date, which is in epoch. And then you have a delay, which is in delay for departures, which means that if you have a negative time, that means that your departure might have left early. And if it's a positive number, then it's been delayed by that many minutes. You have the distance. And then you have your origin and destination airport codes, as well as some metadata that Azure Cosmos DB already puts in. So the first thing to do is to configure your Spark and Cosmos DB connector within your Spark clusters, as you can see here. There are a couple jars we do use in order to make sure that you can connect from Spark to Azure Cosmos DB. For over here, we do have the configuration for the endpoint for Azure Cosmos DB, your key, the database and collection you're using, preferred region if it is set up as a multi-region database, sample size, page size, and then I want to highlight this aspect right here, which is the query. Yep. So this query over here is actually selecting the date, delay, distance, origin, and destination from the collection. And this is being pushed all the way down to the database layer. This is nice because we're able to filter a lot of the system metadata before sending it over, because we want to minimize the data we send over to the Spark clusters. So I can actually take this query and execute it against my collection, just natively through our Azure Document DB Studio. Let me zoom in so everyone can see. Here's the query. Here's, let me just execute it first. And here's the result set. So originally, without having the filtered data, you'll find some of the metadata we normally put into your collection, which are the timestamp, the ID, self-link, e-tag, and attachments. And so we filter it all out before sending it over to your Spark cluster. Over here, we finish the formatting of the Spark clusters. We do a simple count. We cache it and then create a temporary view, which are all done beforehand, before this talk. And then this is actually quite important. So we actually have a file, a text file with the airport codes for the actual cities. This is fairly unique because just for this purposes, we want to show you exactly where it's flying out from. So rather than giving you the airport codes, we want to show you where the actual state is or the location of the airport. But you can imagine that you can actually combine this with other blob storage data, right? So if you have other blob storage data located in Azure Blob Storage, you can combine that with Azure Cosmos DB within your Spark clusters. So the first thing is to execute is a simple count, which is executing right now, as you can see over here by the status. And this is simply a Jupyter notebook set up with Spark on HD Insight. It finished fairly quickly. And you could see in the table, time. Shows on the table. 1 second. It looks like the results are getting hidden for some reason. Okay, this should pop up the results. 1 second. Okay, so that's 33,107 flights leaving from Las Vegas. The key thing to note here is, although I run this query on Spark, I can actually push this down to Cosmos DB to filter out the flights leaving from Las Vegas all the way at the database level, rather than bringing all that data into the Spark instances. For this purpose, I brought everything over because we'll be doing a little bit more complex operations further down this demo. So something I can do is get the top 10 delayed destinations from Las Vegas here. And this is ordered by the pure number of trips. So as you can see here, by number of trips, absolute number of trips, Las Vegas has the largest number of delayed flights, then San Francisco, Chicago, Denver, Phoenix. If I want to see just the absolute number of total delays, so total minutes delayed, I can actually change the order by to rather than showcase trips, I can do total delays. Total delays. And now this query will do the same thing, except it'll calculate the total number of delayed flight, or total number of minutes delayed for each city, and it could showcase it. So San Francisco, just the number of flights leaving from there, the total number of minutes delayed is the highest. Then Las Vegas, Denver, Chicago, Phoenix. And so now we can also calculate the median delays by destination cities departing from Las Vegas. As you can see here, something to note out is Cosmos DB does have simple aggregation support, so you can do your min, max, sum total, or min, max, sum count. But for the more complex ones, such as median, you can pair up Cosmos DB with Spark in order to do these medians, which is the 50th percentile, and you could do the 75th or 90th percentile, whatever you choose. So as you can see here, by the median delay, sorted by median delay, Anchorage actually has the least amount of delay in the median compared to any other city, and then Honolulu, Bellingham. And so this is one aspect of looking at it, but we can also look at the other way, where rather than having it in ascending order, we could do descending order. And you could see some of the median delays by descending order. You can see that Lubbock, Birmingham, Albany, Louisville have some of the highest median delays for their flights leaving out of Las Vegas. And now, the next aspect I want to highlight is, how do I take this departure data, this flight data, and map it into a graph? Just because maybe I do want to interact it more as a graph, it follows more of my mental model. And so we do have some examples here for that. So here, I'm building my data frame in the temporary view as a graph. And then I'm doing some initialization, so I'm creating the vertices as well as the edges. And then finally, you can see that my aggregation as well as query looks more like if I'm interacting with a graph. So you have your trip graph, you have the edges, you're filtering on the source being Las Vegas, and the delays being greater than 0. And then I'm grouping by the source and destination, averaging the delay. So we want to see what flights departing Las Vegas has the most significant average delays. So let me just run that. Execute this. So it's still running. Here we go. And so you can see that Honolulu, by average delays, has the highest, Albany, Palm Springs, Cincinnati, and Lubbock. And then another thing that's very interesting and kind of very native to graphs are, so what has the most amount of neighbors, right? So what's that airport that has the most amount of flights that are leaving out of it? And so we can run this over here, which is basically sorting the number of degrees for each vertex. And here are the number of outgoing flights from these cities that have the most neighbors. You see that Atlanta has the most, so highest number of degrees. And then you have Dallas, Chicago, LA, and Denver. And then other questions you can ask on this graph is, are there any direct flights from Seattle to San Jose? And so this is just a simple breadth-first search from Seattle to San Jose, where the max path length is 1. So it's just one neighbor away. So as you can see here, there are a number of flights leaving from Seattle to San Jose. And then what happens if I choose a more obscure location, like Buffalo? Are there any direct flights from San Jose to Buffalo? And this, once again, is using the max path length equals to 1, which means that Buffalo as well as San Jose are neighbors. So the result is an empty set, so there are no direct flights. So what are the connecting flights from San Jose to Buffalo that we can look at? As you can see here, there are a number of connecting flights from San Jose to Buffalo, but this is not very useful just because I still need to parse out the data. Which means the next following a question would be, what's the most common transfer point from San Jose to Buffalo? So from here, you can tell that the most common transfer point from San Jose to Buffalo is Las Vegas, which makes a lot of sense just because it's close by to San Jose, and then Chicago, Phoenix, New York. And so for the next part, I'll go into something that's already run just because the ML algorithms can take a little bit long to run. But this is where it becomes much, much more interesting, right? This is where we can do some of the predictions for, will this flight get delayed based on certain parameters, right? Like weather data, or time of day it normally leaves, or depending on what the flight number is, what the plane is. And so from here, within the Jupyter Notebook, rather than running it, I'll walk through what happened. First, preparing the data set. So when you're working with this type of data, you do want to prepare the data set in a way so that you optimize the performance of the ML algorithm. Some of the things to consider are, once you're working with the terabytes worth of range of data, you want to make sure that you do push predicates down into Cosmos DB so you filter your data so that everything can run as fast as possible. Other things to note is you do want to vectorize your algorithm. And so for this logical logistic regression, which is essentially, was this flight delayed or not? Yes or no? You do want to change that categories into vectors, right, to numbers, because this is why a lot of different machines that are used for machine learning uses a lot of GPU, right? Because it's number-based. And so if you want to run algorithms faster and faster, people always promote get bigger and bigger GPUs, get more of them. And so after preparing the data set over here, I do the encoding into the vectors. And then I create a data pipeline. And then based off of the signals I put in, which are the features, distance, origin state, the destination of state, trip identifier, I'm able to, first, I split the data into 70-30. So generally, you want to split your data into your training data as well as your test data, right? And so your training data is essentially what you use to train your model, right? So for my delay prediction model, I want to make sure that I put in data so that my machine learning algorithm can accurately predict whether this flight will be delayed or not. And then I have 30% allocated to the side so that I can put it back into the model and say, can you predict whether this is correct or not, whether it will be delayed or not? And then I could reference it in order to make this better and better, right? The general split that people usually do is a 70-30. So you look at 70% of the data split for your training data and 30% for your test data. And then over here, just using a lot of these Spark libraries, you can do a simple logistic regression. Logistic regression is simply saying, separating into categories. And the categories I decided are binary, just was this flight delayed, was it not delayed? And these were the predictions made based off of the model. As you can see over here, the confidence and the probability it has is roughly 77% for most of these, from the flight to the destination, which is Seattle. It got most of it correct. There are a couple that it got incorrect, which I hope you guys can see here, where the label says it predicted that it will be delayed, but it wasn't. For the most part, you see that it has pretty high accuracy, but to be a little more scientific, we can evaluate our model with the binary classification evaluator. So what is the precision of our model, right? The precision of the model was actually 77%. 77% is not too bad, but definitely can be improved upon. The next thing to do is actually evaluate the model against a confusion matrix, right? Because as you can imagine, I can technically say every single flight will have been delayed, right? And in essence, if I'm not doing a confusion matrix and testing for true positives, true negatives, false positives, or false positives and false negatives, then essentially my model can technically be correct just because I'm saying everything's going to be delayed, and testing it on my data, it says, yes, you got all the ones that were delayed, but on the other hand, you also misclassified all the ones that weren't delayed. And so we do have a confusion matrix over here. You have your true positives, which are, was it on time, and was it predicted to be on time? You have your true negatives, was it delayed, was it predicted to be delayed? You have your false positives, which are, was it delayed, was it predicted to be on time? And then you have your false negatives, which is, was it on time, and it was predicted to be delayed. So we do a couple more things after this, but I'm going to kind of switch back to the PowerPoint deck. But I want to emphasize that this ML model is not, incredibly complex. This is very simple in terms of the logistic regression model to predict delayed flights. So now I want to talk a little bit more about real-world use cases where Cosmos DB as well as Spark can be applied together to get richer insights and deliver a full application experience, right? So if we have the delayed flight model, what can we use this in? How can we better our applications as of today? And so I want to get kind of the minds thinking about how this can be applied to real-world applications. So first things first, as you know with Azure Cosmos DB, we are multi-model. I showed you a little bit about the documents, the NoSQL documents interacting with Apache Spark. This also works with Graph. So you can actually connect Spark with Graph and our Gremlin APIs in order to do a lot of the aggregations and the data science on top of that as well. So diving into healthcare solutions and how Cosmos DB with Apache Spark can deliver different insights and what kind of use cases it can open up. So some of the things to think about are the bed scenario. the bed sensor scenario. So imagine if you had a bunch of beds in a hospital, and all are collecting a lot of sensor information. What kind of application can you have on top of that? This is kind of your classic and canonical IoT scenario. You have a large stream of data from different sources, all emitting the data to Azure Cosmos DB. And this is well suited for Cosmos DB because of the high ingestion rate. This is the same reason why Toyota uses us for IoT. It essentially means that as you have many different sensors, right, 10,000, 100,000 sensors that are writing one data point per second, you can write that all to Azure Cosmos DB by scaling up so that it can handle that number of writes. Other things that it's really optimized for is it has all the SLAs. As you can imagine with any type of healthcare application, there's a lot of risk involved. And so you do want an application and database that has very low risk so that it can handle a lot of the critical paths and have that high availability. And you can build models to interact with the data through our new feature called Change Feed, which came out a couple months ago. And then from there, you can actually deliver a robust scenario application. So some of the things to think about. So imagine if you had your bed sensor information, and from there you have sensors emitting data to Azure Cosmos DB in real time, having all that data there, and then using our change feed for real-time alerts, right? Let's say that from the information you're collecting that you see the bed movement is very low, or the respiratory rate has hit a critical level. From our change feed, you can do alerting on top of it. You can also have certain actions triggered based on the events you see. And then taking that data and pushing it back into your Spark instance, you can actually deliver more insights as to what kind of combinations of sensor data, what's the patterns of sensor data, where we should trigger certain events because something is happening where we need to take action, right? And the key thing here is, so why Azure Cosmos DB? What's the real purpose of having Azure Cosmos DB there? Well, first, it's a persistent data store, so you want to make sure that you have your data saved almost immediately. The second thing is it's almost real time, right? So real-time alerts is actually a big thing. I don't know how many people remember from my overview session, but you can imagine with Toyota when they want to light up some type of OnStar support, right? You get in a vehicle crash, immediately the ambulance and are all notified that there's an action has been triggered over there, where your GPS location is, have help come immediately. Same thing with here. So with that, you need a fast database that you can trigger so that you can have the real-time alerts and you could have action taken immediately. Another thing to think about is the operating room scheduling. As you can imagine, in a hospital, there's a lot of specialists, people who are very good at certain aspects within the medical field. And when you're operating on someone, there has to be this strong coordination of people coming in, helping in different times. And this type of coordination is very difficult, right? The efficiency is dependent on just who the staff is, as well as the allocation of what they're doing. And this is kind of your classic problem of how do we make sure that this scheduling is done in a proper way so we can maximize the time and efficiency across the board, especially when you're working in a fairly large hospital with a number of moving pieces happening. As you can imagine, it's not just strictly dependent on the staff. It's also dependent on the facilities within the hospital that are available, right? So you have your OR, you have your x-rays, you have all this machinery, where if someone else is using it, how do you schedule that appropriately so that everything moves in a smooth, streamlined manner? Better utilization always means better profit margins, reduced support, maintenance costs, and so the number of benefits from using Cosmos DB plus Spark for a lot of your data insights can lead to a lot of operational overhead that's saved. And overall, the takeaways would be that with better medical staff efficiencies, you have better outcomes, you have shorter waiting times and less cancellations, and overall, you can improve the efficiency of the hospital. And so this is a little bit of a diagram that showcases that if you're trying to get an elephant in between the hours of 7 a.m. through 6 p.m., you do have to understand that this takes roughly 11 hours. And so you can try to squeeze it in earlier, but it requires more people, requires more management, and it usually leads to more chaos and more inefficiencies. But if you're able to schedule it beforehand properly, if you're able to set aside the right amount of time, have the right resources, you can increase efficiency. And so I have just this little diagram to showcase just what kind of benefits it could have in the medical field. So this is talking a little bit about how you can have a lot of the events, the alerts, all pump in data to Azure Cosmos DB. Once again, you can leverage that change feed functionality to get real-time notifications, alerts. You can have the automatic rescheduling based off of what is happening in terms of the alerts, as well as the different events that are being pumped into Azure Cosmos DB. And then you could have ML algorithms to help predict the scheduling availability, help the coordination. And this is, in general, with any type of ML, your ML algorithms get better over time, right? And so you can't imagine having immediate results right off the bat. But as you're building more of this data, historical data, understanding where the inefficiencies are, your ML model will get better over time. And so now it can predict with more certainty on how to do the scheduling to reduce the inefficiencies. So this is talking a little bit more of a specific use case within the medical field, which are genomics. Right? Kind of the classic one when people think about when they think about machine learning. You can imagine that you will have, within genomics, you have your FHIR, which stands for Field Health. I wish I could remember the acronym. Does anybody remember the acronym for FHIR? FHIR? Slipped my mind. Okay. But you can use this data, which is natively JSON data, to actually move into Cosmos DB, and then you can trigger a lot of events based off of it, as well as get a lot of insights based off of it. So the use case that comes into mind is having this data, combine it with your lab data, your treatments data, as well as your responses data, and then on the other hand, having the genomics data, which are more classified with the VCF, the BAM, SAM, as well as the FASTQ. And combine that data both into Spark so that you can get deeper, richer insights for medical personalization for users. Right? Overall, you want to make sure that the medical practices are catered towards each individual. So combining a lot of the data that you have in the hospitals, as well as your primary care provider, combining that with the genomics research that's happening both in Spark, you can have real-time personalizations for users within hospitals. Having this type of real-time personalization will make practices much more efficient. Overall, you can imagine that costs go down once you have higher efficiency. And this is a little bit about how you're able to use ML to almost revolutionize a field. So once again, why is Azure Cosmos DB really there? Right? Does it why is it not different from any other database? Why does Azure Cosmos DB really need to be in this architecture? Well, one of the key things with this is the latency once again. When you do have practices, latency is key, right? And having learnings and applying those learnings in real time is also key, and it's a priority for a lot of our customers. And so most of our customers who come in and say, we're going to do benchmarks against you, against other Azure services, data services, and figure out which one's the fastest so that we can give these insights as fast as possible. The other key reason why Azure Cosmos DB is such a great fit here is that we do have a high availability, as I mentioned before. We are 99.99% available, and we guarantee that through an SLA, which is our promise to you. And that's only within a single region. Right? So we do have global distribution so that you can increase that even further by replicating your data from East US to West US, all the way to different continents like Asia, Australia. And we make it our priority to have our database always up and running so that mission-critical applications like this, especially in healthcare, even IoT with vehicle notifications if there's a crash, are always available. Right? And this is one of the key reasons why there are a lot of individuals coming to us saying, we need that database that can't have any downtime period. Right? And nowadays, it's not even for medical reasons. Right? You can imagine any type of mission-critical application for your core business going down for a week your database going down for a week, a couple of days, will have major impact on revenue. So overall, using a database with that high availability, that global distribution, combined with the low latency really makes this an attractive offer for combining with Spark for the machine learning purposes for a lot of applications out there, especially when they have a real-time requirement. And this is not just scoped to healthcare or different medical practices, how ML and Cosmos DB can help. There's actually quite a few scenarios out there, just off the top of the head, that can really be impacted by this. You have your fraud detection, right? A lot of websites today, their new user sign up has to be as streamlined as possible, right? But how do you make sure that you get rid of the fraudsters, the criminals, right? How do you make sure that on the fly, when someone's signing up, you can make a call on whether this person has a high probability of being a fraudster or not? And this needs to be in real time, right? You can't have a sign-up page that says, thank you for signing up. We'll get back to you in 2 to 3 weeks just to make sure that you're not a fraudster or not, right? Can you imagine what the conversion rates are there for any popular website doing that? And that's just being fraud. That's just fraud detection. That's just fraud detection. Other things are real-time recommendations, right? You can imagine if you're on any e-commerce site, let's say jet.com, based on your past 5 actions, past 10 actions, can we make good predictions for what you want next, right? Based off of you looking for socks and shoes, can we predict that you're looking for another item? And this is based off of your actions, right? As of today, how it's normally done is it's based off of similarities of products, right? So if I'm purchasing headphones, usually they'll recommend me other headphones, right? But based off of that behavior, we can probably make even better predictions, right? So if I'm getting sandals and swimwear, maybe we can make a prediction that, oh, this person is most likely going to a pool or a beach. Maybe we should advise them to get sunscreen, right? Or a beach chair. And so this is where real-time ML can really help out. And as you can imagine with any website, as the latency goes up, the conversion rate of customers looking to purchase their items goes down, right? So you need to have that real-time ML combined with Azure Cosmos DB, which is the persistent data store, so that you can increase conversions and you can have a very personalized website in real time. Vehicle telemetry, again, as I mentioned before, the OnStar one is a classic one, but there's many more, right? Any type of real-time alerting. I think one of the big things today with ML is smart vehicles, right? Smart vehicles happens all the time. People are looking at how vehicles can drive around different cities, different areas. But the key thing is, how does that vehicle, when coming to a question that it has a hard time answering, how does it traverse an ML algorithm, right? So one of the things that I always, I think we talk about is, if your vehicle is going down the road and, there's something, there's an obstruction in the way, at the time, does it make the call to move off, go onto the sidewalk where it might have higher risk, or run straight into the obstruction in the street? So these are some type of real-time ML questions that come into mind, whether, how does it make that decision process, as well as what is the database that can help it so that it can make it within a split second. And lastly, just kind of another one is the customer service, right? The customer service industry. When you go into a website and it says, hey, please chat with a representative, and they'll ask you a select number of questions and you answer back. And how does it actually make those responses in real time? How does it know what to ask you next? How does it know what you're looking for, what the right answer is? Right now, it's fairly naive in terms of how much deeper it can get with using a richer ML algorithm, but this is just the top of the surface. This is evolving every day. And having that persistent data store where it's taking in all the comments, taking in all the questions, and constantly adapting the ML model so that it can make better recommendations to you, so it can better pinpoint what your problem is, so it can better streamline your experience as a user on these websites is key. So overall, this is just a couple of real-world scenarios that come into mind, but it's kind of just the beginning. I'm sure every one of you here can think of something where ML would really streamline the process, where it can really improve the application, the overall customer experience. So One of the call to actions is we do have a free trial or tryout, which is try Azure Cosmos DB. So if you are interested and you haven't used Azure Cosmos DB, I recommend going to the site. We lease you an account, a full account, for 1 day, and you can extend it to 2 days. So definitely try it out. See if it fits your needs. See if it really covers the scenarios you're looking for. I definitely recommend pairing it up with Spark just because it opens up so many use cases. And we do have documentation on that so that you can try out different Spark algorithms on top of it and figure out what you can do with Spark with Azure Cosmos DB. So these are some of the sessions that we still have left. We have 2 sessions, one on Azure Cosmos DB design patterns and case studies for globally distributed applications. And the last one is Internet of Things with Azure Cosmos DB. I recommend going to both of them. And thank you for your time, and I want to leave the last roughly 15 minutes for questions and Q&A. Perfect. And I think the mics, are they live? Okay, perfect. So if you can just, if you have a question, feel free to come to a mic, and I'm happy to answer. Awesome. Thank you so much for your time.